Recently, I've been thinking a lot about education and its importance in our lives. And I found three quotes which summarize my thoughts and ideas around the topic.
Cause the players gonna play, and the haters gonna hate.
Thanks, Taylor. And she's right about things changing. Education is a tool for change. And so we're going to embark on a journey to learn about change. Or its more intimidating name, calculus. Deep down, calculus is the mathematics of change. It helps us understand speed, acceleration, how things change over time. We don't live in a static universe, so it's really important to understand what happens when we change things. Without calculus, we could not have sent a man to the moon, use our phones, or develop life-saving drugs and treatments. Calculus is the ultimate tool to describe and understand nature. It's a very intimidating topic when you first meet it, and I hope by walking through the history of the subject, meeting all the pioneers involved, and understanding their motivation and intuition, everything will start to make more sense. Our journey into calculus begins on the floodplains of the River Nile. The ancient Egyptians were a great civilization, and their study of mathematics mostly focused on concepts in geometry, and they used this to build the magnificent pyramids. A problem they faced was the taxation of land for living and farming. They needed to know the area of shapes, like a rectangle or a triangle. But the shape that eluded them most, and many other mathematicians after them, was the simple and humble circle. And the area of the circle does give a strange result. You may remember from school that the area is pi r squared, where r is the radius. But what is this pi? There are many possible interpretations of pi. For example, the ratio between the circle's perimeter and its diameter, or an infinite decimal with no repeating patterns. The story behind pi is very rich and quite fascinating, and this number appears in many unexpected areas of life and nature. But we'll have to dive into this another time. The Egyptians had quite a good approximation to pi, 256 over 81. But it was really the Greeks who found an interesting way to calculate pi and the area of a circle, and the ideas they used formed the first building blocks and motivations behind calculus. So let's head over to ancient Greece to meet Thales, Pythagoras, and their contemporaries. To get into the mood, we have to unfortunately picture ourselves in a boring maths class, which shouldn't be too hard. And what do we do when we're bored in class? We doodle. So we start off with a circle, and we start drawing shapes inscribed within the circle. A square, a pentagon, a hexagon, and we keep on adding more sides. But life is too short just to keep on drawing regular polygons. So we take a minute and we look at our drawing, and we make an observation. It appears that the difference in area between the circle and our shape, i.e. the purple area, is decreasing as the number of sides increases. And it turns out this is true, and it's not too difficult to show. Our shape starts to look more and more like a circle. This is the way the Greeks were thinking about the area of the circle and more general shapes. This strategy, often referred to as the method of exhaustion, is a key motivation behind calculus. By exhausting the area of the circle with regular polygons, we find better and better approximations to the area of the circle. It's important to note we can calculate the area of the polygons by breaking each polygon down into triangles whose area we can compute easily. So we now ask ourselves, could the circle just be a polygon with a large number of sides? After thinking for a while, it turns out this is not quite true. Okay, a little setback. Well, we know the area of the polygon gets closer and closer to the area of a circle as the number of sides increases, but never equals the area of a circle. So we muster up some courage and we ask ourselves, is a circle an infinite-sided polygon? And if your brain is hurting now, don't worry. It's a ludicrous question to ask, but also at the same time a very important one. Ludicrous because an infinite-sided polygon doesn't really make sense. What does that even mean? But it feels right in some weird, twisted way. The polygon looks more and more like a circle as the number of sides increases. This example highlights three of the most important concepts in calculus. I'll let my friend Paul McCartney introduce the first.
I'm getting closer. I'm getting closer to your heart.
Thanks, Paul. In this example, we're looking at the idea of a limit. This concept of getting closer and closer to, but not quite reaching. We're looking at the extreme scenario. We're also looking at a big infinity, namely the number of sides of our polygon, and seeing what happens when we keep on increasing the number. We're also more subtly looking at a small infinity, and by this I mean an infinitely small quantity. And here this is the difference in area between our circle and the area of our polygon, which keeps on getting smaller and smaller, but always stays positive. We're going to think slightly differently now, and it begins with a simple question. What is number? It may seem like a basic concept right now, but it actually took thousands and thousands of years to define and truly understand. Historically speaking, counting and the use of numbers was for keeping account of the number of sheep or pigs you have, and now maybe it's the number of retweets you get on Twitter. But then what about zero? Zero is a difficult concept because we think of zero as a quantity. How can nothing be something? And then we have fractions. Half a slice of pie. I ate 5 out of 7 slices of pizza. And then we ask ourselves, are there other numbers? And the answer is yes, there are. So I hope I've convinced you that the idea of number is not so obvious. And the first traces of calculus actually begin with this very question. The ancient Greek concept of number was quite natural and intuitive. They just considered numbers to be the whole numbers, 1, 2, 3, and so on. And now you may ask, did they have some concept of fractions? Well, it turns out they did, but it wasn't quite a fraction. They didn't think of it as a number, but more of a relationship, a ratio between two whole numbers. And they defined it like this and called it commensurability. Given any two lengths, A and B, I should be able to find a fundamental unit, let's call it U, that fits exactly a whole number of times into both A and B. But that's enough about numbers for now. Let's go and meet some people. The Pythagoreans were Pythagoras' merry band of followers, but they were also his students. But really, they were a cult that worshipped numbers. They believed all is number, and that they could solve the greatest riddles of the universe just using numbers. They treated numbers like they were gods. They also had rules for everything. They had something very similar to our 5-second rule. How long a piece of food can be on the floor before it becomes inedible. His strangest story, though, is that he gave up his life to protect beans. You see, he would never touch beans because he believed that they would cause flatulence. And whenever you release that gas, it would take a part of your soul away too. This actually led to his demise. The story goes that the Greeks were very unhappy with Pythagoras, so they decided to burn down his house while he was still inside. Now naturally Pythagoras ran out screaming, and he kept on running till he approached a bean field. And he was so adamant that he would not touch or eat a single bean that he stood there and let the Greeks catch up with him, who eventually chopped off his head. And the craziest thing about Pythagoras was that he killed a man. Whoa, that's not cool. That's a crime. But we'll let him keep his sunglasses because he looks pretty cool. Yes, he killed a man called Hippasus, his own student, because Hippasus had discovered something wrong with Pythagoras' definition of number. And Pythagoras could not let this stand. He could not let anyone find out. At the time, they were both out at sea, and Pythagoras threw him overboard. We'll see how Hippasus discovered a new number in a short while, but I first want to show you a proof that all mathematics students see, that the square root of 2 cannot be written as a fraction. We'll start off with the notorious Pythagoras' theorem, that the sides of a right-angled triangle, A, B, and C, where C is the hypotenuse, satisfy the equation a squared plus b squared equals c squared. We'll simplify our situation by letting a and b equal 1. So then c squared is equal to 2, and therefore c is equal to plus or minus square root of 2. And because we're dealing with lengths, we take the positive square root. We're going to use a strategy called proof by contradiction, where we assume what we want to prove is not true, and show that the consequences of this assumption cannot be possible, i.e. are false. So we're going to assume root 2 is equal to a fraction, m over n, where m and n are integers, and n is not equal to 0. We can further assume that m and n are both not even, because if they were, we could simplify our fraction. So then we multiply both sides by n, and then we square both sides of the equation. So this means that m squared has to be even. From this we know that m has to be even. So we can write m equal 2u, where u is another integer. We can substitute this into the highlighted equation, and we get our new equation, 2n squared equals 4u squared. And we get n squared is equal to 2m squared. But this means that n is also even. But that's absurd. Our justified assumption was that both m and n are not even. And this is the contradiction. We assume whatever we want to be true and show that the consequences of this assumption lead to something false. So now we're going to return back to Greek ideas and how they thought about commensurability. We're going to be in the exact same scenario with our right-angled triangle, with a particular focus on the base and the hypotenuse. First, let's recall the definition of commensurability. Given any two lengths, for us the base length and hypotenuse, I should be able to find another length which we'll call the fundamental unit, that fits exactly a whole number of times into the base length and the hypotenuse. We're going to do the same proof method as well, a proof by contradiction. And so we'll assume that there is such a fundamental unit that fits exactly into the base and the hypotenuse. Now the idea behind the proof is really neat. I'm going to leave out the finer details and put them in a blog post, but the key idea to understand is we can construct smaller and smaller similar triangles whose lengths are always whole multiples of u, our fundamental unit. Eventually though, we'll be able to construct a triangle whose side lengths are all less than u. And this is the contradiction. Each triangle we had, we knew that the side length were whole multiples of u. But this can't be possible if our triangle has side lengths less than u. When this idea was shown to Pythagoras, he thought, maybe if I choose a smaller u. But that's what's so cool about this proof. We never actually made a definite assumption on the length of u. It could have been anything as long as it was positive, and the conclusion would have been the same. And so we can only conclude that there is no such u possible. So how does this lead to any ideas in calculus? Well, when Pythagoras was trying to find smaller and smaller u to show that the two lengths were commensurable, he eventually started to think about extremely small quantities, something smaller than any positive number, but greater than 0. A quantity so small that it looks no different to 0, but when you add it up infinitely many times, you get something non-zero. Now, Pythagoras and the Greeks hated this, and with good reason. It feels very wrong. It makes your brain hurt just thinking about it. They couldn't get their heads around it and abandoned this idea. It was only in the 17th century when mathematicians started toying around with this idea again and started thinking about calculus in these terms. We also notice that this example has a lot of similarities with the example with the circle and our polygons. This idea of getting closer and closer to, that hunt Pythagoras was doing to find that fundamental unit, but also this big infinity, the number of triangles and fundamental units he was considering, and also a small infinity, the fundamental unit itself kept on getting smaller and smaller in the hope that one would actually work. These three ideas form the first building blocks of what became calculus. Next time, we're going to dive deep into this concept of infinity and meet a man who believed that the universe was static and that there was no such thing as motion. Thank you so much for listening. I would love to hear your thoughts on what you liked and even on what you didn't like. You can leave a comment below or drop me an email. See you next time.